All right, so welcome back. Today in this video, we're going to be continuing our review in water resources and environmental engineering. And the topic specifically for today is going to be stormwater. So I have a few practice problems for you all, and I want to dive right in. Okay, so a lake is evaporating. Determine the lake evaporation if the pan evaporation is 8 millimeters per day and the pan coefficient is common. Okay. So what information are we given? Well, we are given that we're given the pan evaporation. And we are given the pan coefficient is common. Pretty much it. And the lake is evaporating, right? Okay. Find. All right, what are we trying to find? The lake evaporation. Okay. So I'm just going to search. I don't know what the heck is going on. So I'm just going to search lake evaporation. Okay. One thing comes up. Cool. So I go look at this. The lake evaporation EL is related to the pan evaporation by the expression. Okay. So EL is equal to PC. And what is PC? Pan coefficient ranges from 0.3 to 0.85. Common is 0.7. So, okay, we know PC. We know it's common, right? Which is 0.7. And then EP. What is EP? EP is the pan evaporation. So do we have the pan evaporation? Yes, at 8 millimeters per day. So we are going to say, formula needed, EL is equal to PC times EP. PC, what's the value of PC? Well, it's equal to 0.7. And then what's the value of EP? EP is going to be 8 millimeters per day. All right, so now we're just going to multiply these out. So you get 0.7. Lake evaporation is equal to 0.7 times 8 millimeters per day. And so when you do that, I get my lake evaporation to be 5.6 millimeters per day, or C. All right, pretty simple, straightforward. Look at number 2. Assume the pipes are all at the same elevation. Given the image and data, what is the head loss in BC? Okay. So we are given the flow, right, going into the pipes. We got a flow of 17.5 cubic feet per second. And then we're also given the head loss in each of the different spans. So they tell us that the head loss in from A to B is going to be 0.233, right? Okay, they give us the head loss and from the span from D to A, right? Okay. That's 0.0335, and then they do the same thing for the span from C to D. Okay. All right, so what do we need to find? We need to find head loss in B to C. All right, so formulas that you need to know. One thing in a system, so there's not a certain, I guess, formula that you need to know. It's a prior knowledge type thing, or there's not a formula that you can use from the handbook, but you do need to understand that in a system, the sum of all of your head loss should be equal to 0. So I'll show you what I mean. So the sum of the head, just took a L there. Sum of the head loss is equal to 0. So the head loss from A to B plus the head loss in B to C plus the head loss from C to D plus the head loss of A to D should all equal to 0. Okay. But this all depends on the direction of flow. So just imagine, it's important to note where this water would be going. So we know if it's coming in at 17.5, right? If it comes through point A, right, which is what it has to do, the normal direction of flow is that way. The normal direction of flow is this way. So go from A to B or A to D, right? Now, when it goes from A to D, what does it then do? Well, it's going to go from D to C and outwards, right? Okay. If it goes from A to B, and then what does it do from B to C? Well, some of it goes out. Some of it it's probably going to continue. Maybe it could go either way, right? But you would think if it's going from A to B, it's probably going to go from B to C and then out. But you never know. Go either way. They are going to split. Either way, the flow going in is going to be the same going out. Similar to the sum of the head loss happening, it's all going to be equal to 0. So you want to look at this as the sum of each head loss. So let's look at from, they give us from A to B. So I know that the sum of the head loss, sum of the head loss is equal to 0, which is equal to, okay, we got the head loss in A, B, right? A to B, that's natural, and that's the typical direction that would be going, okay? Plus the head loss in B to C, right? Minus, right, the head loss from C to D, because from C to D, it's not going from C to D, it's going from D to C. So it's going in the opposite direction. Okay. And then what about the head loss value from D to A, right? Well, again, D to A, it's not going from D to A, it's going from A to D. So it would be minus head loss from D to A. All right. Now let's put these into actual play to get our variable that we need, which is going to be the head loss in BC. All right. All right. So the head loss in AB is equal to 0.233 plus the head loss in BC minus 0.052 minus 0.0335. And so some of my head loss, or go to 0. Yep. So H of BC is equal to, once I bring it to the other side, I get it to be negative 0.1475. So that just means we drew it the wrong way. But either way, it's in meters. So it's going to be C. All right. So that just means that the way we drew the flow, it should be going this way. Right. So we can get rid of this. Okay. Let's look at number 3. How do best management practices, BMPs, contribute to enhancing the stormwater quality? So, given a BMP, find how it enhances stormwater quality. Stormwater quality. Okay. Any formulas needed? No. This is a conceptual question. So, does it increase the stormwater runoff velocity? No. You don't want water moving fast. That means it could potentially create more flow, more velocity, more force, which could damage pipes and all this other stuff, which could cause flooding and different things. So that's not a best management practice of water, right? Or stormwater quality. By reducing the volume of stormwater runoff, no, it's not doing that. You really can't control the amount of water because it's going to rain, it's going to do whatever. Once you design those basins, it is what it is. You just need to design them for literally the maximum amount of water that could potentially happen in a storm over time. Okay, by capturing and treating pollutants from stormwater, yes, BMPs definitely do this. And I wrote some notes, basically that BMPs play a crucial role in improving stormwater quality by capturing pollutants, right, before they can enter the natural water bodies. These practices include various measures such as, okay, you got vegetative swales, that maybe swales are kind of like a ditch where you got water, and this is a cross section of the ditch where you have water you know, kind of filling up there, but you got this grass, right? Vegetation, right? Where grass is in there, and then those leaves and all that stuff is collecting the nasty dirt, or the dirt will get collected, the leaves will get collected, whatever stuff, and then the groundwater will trickle on down, and it kind of creates this water seeps on down, or goes and has a pipe of some sort, or it goes on through. Okay. By diverting stormwater to natural water bodies, I'm sure that that's a decent answer. But the way that they grade and different things is a little different. So C is your best answer. All right, so that concludes stormwater. In the next section, we're going to be looking at collection systems. So I'll see you in the next video.